I'm Doug from not Sunnyvale, but Mountain View / Moffett Field in Ames. I've been my current claim to fame is the flight software author of all the interfaces to the LADEE payloads, as well as the star tracker. And the interfaces mean the hardware I/O modules. Talk to the hardware and put data on to the software bus. We'll get to that later. Scott, Krista, and Craig Paris were key contributors to the overall LADEE architecture and the infrastructure to support all of these interfaces and stuff. So they were key on making a lot of the decisions as to how to utilize this lunar laser communication. Like, how do you fill 40 megabits of data and still do everything else your CPU needs to do? That's kind of the problem that this talk is about, but I'm going to talk about a bunch of other things along about how the life cycle of development for LADEE and some of the philosophies that led to decisions along the way. What we won't cover is really extensive, anything detailed on the space to ground of the laser comm. I'll leave that to the guys at MIT, and in particular, Don Borison, who's listed up there. That was the first thing he wrote on lunar laser communication demonstration, first paper he has there, and there's a bunch of things on the web now to get more information on that. I'm going to be focusing on more of just the interfaces between the flight software and the laser comm device. And okay, and then I don't think I defined the LADEE acronym. So the only way I can do that is with a short little song that I made up for my son to explain what I'm doing at work. So it goes something like, model-based common bus, lunar atmosphere and dust, environment explore. Hey, laddie, laddie, my little spacecraft, come on now, let's get busy with your attitude quaternion. Oh, hey, laddie, laddie, my little spacecraft, point me in the right direction. And then it talks about the payloads. Laser comm to ground control. Power me up and now I'm ready to go. Laser comm to ground control. Time to let my mega moonbeam data flow. Anyway, that's I thought I'd just try to get you guys woken up since it's kind of late in the afternoon as the last talk. And also we have a little extra time, although we do have a flight at 7:20 that we're going to be buzzing to get to. Okay, back to the seriousness. I'll try to be serious. I get a little silly toward the end of the day, as these guys know. The three key enablers for the LADEE paradigm that I think were there was the CFE software bus, model-based development, and CCSDS messaging, which kind of tied the whole thing together, and that's what the CFE is based on. And past talks on with FSW from Karen Gundy on the testing infrastructure cover a lot more of these details if you can look at them. And Craig had another one. Howard Cannon, the original flight software lead, who's now the mission director, did a talk as well. I should have put links in there to it, but I didn't get to that. Let's see. Okay. Yeah, we resisted the urge to roll our own. We actually reused the CFE. We made a few modifications and fed them back in, but it's kind of hard not to want to roll your own. The first time you see something new, I was like, oh, why do they need to? I could do this better. But I think we made a good choice in sticking with the plan. Next, okay, this is like kind of the loosely coupled flight software architecture. It's a high-level view. The key points of CFE is it's a publish-subscribe interface, so that modules don't really rely on anything else. They just rely on the messages coming in. And so if you define your outputs, then your outputs and inputs, everybody can go sit down and write all the code they need to do, right? Yeah, right. that would assume that you could do a top-down design and know what all these interfaces are, at the very beginning of your project, which is, as we know, the waterfall rarely works unless you have a godlike knowledge of what you're working on, which means you've done it 100 times or something. But typically, I haven't worked on something like that. So So anyway, looking at this thing here, you see the yellow things? Those are all done in Simulink. No pointers, no things you can do wrong with seeing auto-coded. The things in blue were things that we got from Goddard that were like the CFS, the Core Flight Services. And then so what we ended up hand coding were the things on the side there, which kind of custom to our application commands, telemetry. And the stuff I worked on was inside the bubble hardware I/O. Okay. Okay. Oh, I say back to that top-down, bottom-up thing. So what this kind of architecture allows you to do is do some of your bottoms-up work using the infrastructure at the same time that somebody else is looking at the tops-down, and then kind of meet in the middle as you develop bottoms-up and tops-down, because you don't have to have everything else built. You can start prototyping and defining your interface early on. So that's one of the test early and often is one of the LADEE things. Integrate early and often as well. It's one of the mantras from LADEE. Okay, talking about the payloads themselves, there's 4 payloads. There's a couple of spectrometers. There was an ion detector, that's LDEX, and then the Lunar Laser Lunar Laser Space Terminal. Yeah, okay. The first 2 up there were supposed to be COTS, meaning that they were already like off the shelf, and so we had to, the way it comes contractually, we were supposed to change our interface to match whatever they were putting out. And as it turned out, both of them had extensive code changes along the way. They weren't actually COTS, quote-unquote COTS, but kind of a lesson learned from that was that you can kind of push back on some of these things, but Ames being new to flight software, we're like doing, okay, if you say so, we'll code to match your thing. But as it turned out, I found out that NMS flew on another Lockheed mission, and Lockheed refused to change their code, and they used an Ethernet protocol. And the NMS guys had to change their code to use an Ethernet protocol to talk over RS-422. But anyway, that's just kind of an amusing aside. But the LDEX and the LST were brand new efforts. So we could collaborate and we could negotiate the interface as we started. So the way we developed the interfaces and reduced risk, and the decision made actually above my paid grade, probably Craig and Karen were in on those decisions, was instead of purchasing expensive hardware models of the EDUs and waiting a long time to get them and then relying on ICDs that are perfect to do your coding, after the first few meetings on the phone and it had draft ICD, I took what some people call the suitcase simulator. It had an early version of an EDU with some cables, and we did a little safe to mate and hooked up to each of the payloads and saw what see if we were on the same page with what we wrote on the ICDs, so we could not validate, but at least work through the ICDs. So by the time we were done, we knew that what we had written on the paper matched what the bits and bytes were doing as they went across, talking to each other. And also, the requirements for the payloads ended up coming out of those ICDs. So the requirements came out of a lot of prototyping. So I think it saved a lot of time. There were not a lot of issues with the payloads, and in flight, it's been pretty extremely robust. Okay, and the other thing is, after you connect to the real EDU on the other side, then you can go back to Ames and write a simulator, because now you know your code matches what's on the other side. So you can write a simulator until it works. Because when you're writing the code and you're writing the simulator, you're drinking your own bathwater. But if you've written your code and tested it against the real thing, now you can write a simulator, and if there's any problems, it's in your simulation code. Let's see. Just to talk a little bit about the actual hardware that we're interfacing with, we had the RAD 750. Let's see if I can manipulate this. Oh, wrong way. Oh, there we go. So we get, there's the CPU, there's a CPCI bus, and then there's this board that's called a MOAB or a DMOAB that Craig had talked about. I thought the acronym was Mother of All Boards, but Craig had the official one there. So that's the interface board, and on here there's FPGA's code that allows you to do RS-422 communication and LVDH, high-speed communication. So this was our high-speed telemetry, 40 megabits per second. And this was a channel just for, well, actually, down here there's a ground station and an ITOS sending up a CCSDS message, which gets through some other hardware. And eventually it gets here, and then we can pass it through here and down to RS-422. So commands can come into this thing from the ground and then get up and control the module. Telemetry coming off the module comes down to this control electronics, and then that goes through back down through the CPCI and on out to the ground station. So the cool thing was that most of this is just pass through. I could pass through the CCSDS message over there. This thing isn't working. From down there all the way down to the electronics, and the telemetry for the most part is just coming straight back, and made my job pretty easy. Okay. Okay, so this is kind of a little more text of describing that interface. So we used the CCSDS packets. There's RS-422. And what I'm saying is that, the telemetry that was published to the bus, blah, 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 blah. We used the bus, and we got telemetry from the device and commands coming in. So most of it was passed through, except the one thing that that they wanted was a attitude and time message once per second. So that was kind of generated by the flight software. So this is another look at the architecture there. So if you look at where the state estimator is, that's creating some message that has quaternions in it, and there's a time tag. So that gets on the software bus. If you look down on the hardware I/O apps, there's one called LLCD-IO. It's subscribing to that message, so that gets the quaternion. It has a time tag. Then we can format another message and pass it through the device driver, and it would get to the control electronics. Let's see, back to this page. So that was how we dealt with just the messaging. It was all very simple, just CCSDS messages to the control electronics. Then we also wanted file transfers to get to the control electronics. They wanted to be able to have an ephemeris upload that came from the ground. So we decided a file is an easy thing to deal with. So we'd send them a file. There's also on the control electronics, it was running VxWorks as well. So they had a file system. So we thought, okay, how are we going to deal with files? It's like, why not use the same mechanism that we're using for space to ground? So we got CFDP. We got the same engine, and John Gano, the software engineer who used to work at JPL, but he did all the CNDH for the control electronics, put a wrapper around the CFDP, and we already had a wrapper that Goddard provided with their CF module that wraps bus messages around the CFDP engine, so we can get guaranteed file transfers. Maybe people aren't familiar with CFDP, but if you're not, you can look in the Green Book. They have green books on everything of all kinds of different standards from their consortium. But it's basically FTP through space, but working more optimized for space. And so that worked pretty well. We were able to uplink an ephemeris file. And actually, in flight, they use this interface to uplink a voice of, what was it, Wargo? Mike Wargo, which, if you're into lunar history and research, he's a famous guy. But he had passed away, so they uploaded an MP3 of his voice that got through the control electronics and then downlinked it through the LaserCom, which is kind of cool. Okay, so I think I probably talked enough about that. These are kind of like the details of the high-speed interface, 40 megabytes per second. The hardware FPGA is generating these 192-byte frames with a sequence count and a checksum, which of course we have to strip off on the ground. And then it has this very simple interface, one directional. It's 4 wires, 3 going for transmit, a clock, data, and your frame valid, so the other side knows when a packet starts and when it ends. And coming back to you for flow control is this ready line. So and the hardware takes care of all that. The FPGA takes care of it. All right, so our initial traveling roadshow test, we basically wanted to just verify that the hardware worked and the protocol worked, but we had to write some software. So I wrote some software and basically determined that we have a really bad CPCI bottleneck, which, I mean, looking at that diagram, you'd know right off the top. Trying to fill the 40 megabit per second link, basically use the entire CPU. And we only verify about 30 megabits. The ground software on their side crashed at that point. But so at that point, we verified the hardware. There's a little problem with some of the cabling. We had to use a bob. Went that back to the vendor. They fixed it. And then we decided, OK, how are we going to actually feed this link? Now, and so we're like at that point, we were to have, OK, our constraints are that we don't want to interfere with the CPU because it's got to do a lot of control. It's got to point in the right direction to hold steady enough to basically hit a sheet of paper from California to New York, and the paper's not facing you, it's sideways. So we can't use a lot of CPU. We want to maximize the amount of data, and we probably don't want to do this in real time, obviously. You can't generate data fast enough to do that. So it's got to be some kind of stored data. And the other constraint was there wasn't a lot of time to develop the software for this interface. We're on a pretty tight schedule, so doing anything elaborate was not an option. So let's talk a little bit about how LADEE stores data. Because obviously we want to, at this point we're thinking we want to downlink stored data and stored in files. As Craig had alluded to, there's a SD-RAM, which all the data is stored on. It's powered on all the time, ideally. I think it's been, may have got powered off once. OK, yeah, we had a CPU reboot, but that's still on. So it's basically a file system. It's a DOS file system. It's partitioned. There's a partition for each of the instruments. There's a partition for some test data, blah, blah. It's a gigabyte. And then the way we dealt with the ground, as I talked about, we use CFDP to transfer files up and get files down. And that's kind of the main go-to way that we're doing operations. Science data, the instruments, the ALDEX, and the spectrometers record a bunch of data into their files. And then after they come around from the dark side of the moon, they get a chance to download one of their files, and they each get an orbit. So it take a long time. People always said, well, why don't you use the laser comm to get all that data? It's like the laser comm's an experiment. We weren't sure it was going to work. So that's the way the mission was planned, and that's the way the mission is operating at this point, gathering science data and downlinking our CFDP. So then the thought became, Howard was like, why don't we use CFDP? We're using it everywhere else. Because that's the idea, is try not to write new code, use something we already have. So if you look at that, again, the CPCI bottleneck is even worse, because you have to not only go over there to get the files so that you can manipulate them and put packages on them, then go back over the CPCI bus to get down the laser comm. So that obviously, in theory it sounded nice. You don't have to write any code, but it would be a non-trivial CPU utilization. So what did we finally come up with was basically to do something similar to what Eddie was doing with DMAs, but it was more of a, he's keeping up with a lot of real time and keeping it not filled up and a lot of details. This was very simple. It's basically, we said, why don't we just get an interface that the FPGA implements that we just pass a start address to and an end address to, and let it just send all that data out through this big gigabyte of memory. We can put the pointers wherever we want. And when it's done, send an interrupt to the CPU. And so that's what we ended up implementing, so that the device driver basically just has to sit there and listen for an interrupt. When it does, we added an option to do looping, so that you could loop the same data, because we weren't sure if it would be reliable. Thought we might have to downlink the same partition a bunch of times. As it turned out, there's not even an issue at all. First time you turned it on, it locked on, and all the data coming from us, as well as the data sending on, has been unbelievably reliable. But anyway, there's that looping flag. That's all the device driver needed. As far as ground commands, it was just start and stop address. The only dangerous thing was that you had to make sure that your start address and stop address aren't too close together, because then you get a flood of interrupts from this thing. So that was protected both in ground commands by not allowing that to happen, and as well as in the hardware I/O module. when it would never write something to the driver to do that because there's code for that, and we tested it. Didn't actually do it in the driver itself, mostly because it was harder to get access to that code, and you had to test it on the actual flight hardware. Whereas I could do all the other testing using software simulations, in an environment similar to what the last guy was talking about, and make sure that we're not going to have a little thing that puts us into an interrupt flood and makes us reboot. And then lastly, after you get what we have to do then is we have these DOS file system. We could figure out where the start and end pointer are because we're actually declaring it in the VxWorks. We just make them so they're aligned properly, have to be 4-byte aligned, and then some multiple of 192. The frame size is nice. So we set up these partitions in there. Then to download it, we just send a command saying start, address here, and address there. And it all comes down in this a bunch of frames come down. They come down to the ground. And then we get this big binary file of data eventually. As it gets it's funny when we were testing, we were getting all the data across, and we were almost getting it to the workstation to do my test. And we spent like 8 hours because out there at MIT, they had decided to use Ethernet hardware for all the transports, but not use the Ethernet protocol. They wanted something smaller and more efficient. Like the first byte was a size or something, just a type and a size, which worked fine on most Ethernet cards, but some new Ethernet cards actually look in there and see if there's something screwy because somebody could be spoofing you. So what was happening was that the computer they had designated to get this data and send it across to the workstation where we're logging the data had a new Ethernet card, and we're like scratching our heads. I was like going through all the diagnostics and saying, well, it should be working and blah, blah, blah. And then that was finally the last thing. And the solution at that point was to get an old laptop that had an old Ethernet card, plug it in, and everything worked fine. And then Don Borison walked in and said, you can get data all the way from the moon, but you can't get it across the room. But anyway, where was I going at? Oh, yeah. Okay. We finally got the data across the room, and it's over here in a file. You got to strip off all those headers that have the checksum and the sequence counter in it, and then concatenate it all together. And then you use a couple of Linux commands to mount a file partition as a DOS file partition. And voila, you have this directory that you can CD into. You can cat the files. You can, so if there's CSVs, you can open up Excel. You can do whatever you want. And it's just like you're on the satellite looking at all the data, which is kind of cool. Okay, and then operationally, that's kind of how it was used. I think I may have probably already said most of this stuff. And the thing at the bottom there is originally, the estimates for LADEE for the power consumption was very conservative, as it well should be. And the thought was that LaserCom has this heater that has to stay on in order for it to work. It was using a lot of power, so the decision was to run LaserCom first so they could turn the heater off and then run the other science experiments. That's the reason that the plan is not to use LaserCom to get all this science data. It's to use, was it 128K downlink?
On a good day.
What is it? 100.
No, it's 128K downlink.
Okay, the downlink. Yeah, not the LaserCom. It was 128K on a good day from the moon. So and they're generating. As it turns out, they're getting all kinds of dust events. That interface is event driven. So whenever they get a dust particle, we get a packet generated and we log it to a file. So there's more data being generated that can be downlinked over this 128K link. So anyway, it turns out that the power, there's actually plenty of power, so they're keeping the heater on. So there may be a chance at the end of the mission to run the LaserCom again and clean up and get all the science data that wasn't gotten before. There's some interesting things. The mission of LADEE, the original mission of LADEE was an ecological mission to get a baseline on the atmosphere and the environment of the moon before humans start going and landing things and changing it. So the interesting thing too is that we're doing that now. We're getting all that data, and I've heard that the Chinese are supposed to have a lander landing. Yeah. Is it today? Actually, today. So we're going to get some really good data as to how the ecology changes just from that one landing and stuff. So it's all exciting stuff. So that leads to the last one at the bottom. Yesterday I thought that they were going to run it for sure because it seems like a no-brainer. But when I ran this by Howard Cannon, the mission director, he's like, "Do you know something I don't know?" And I was like, "Well, no, I'm sure I don't." He's like, "No, that's not in the official plans, but I'm pretty sure that's going to happen. My money would be on it happening." Okay, then future implications. I mean, this is just what I wrote here is just limited by what I could think of in a few minutes. And right now I'm working on a constellation of CubeSats. So I thought, hey, this would be cool for all these CubeSats to just use their UHF antennas and have a laser comm node that's like a little LADEE or something sitting there. They could UHF all their data to, and it could store all the data and just downlink it in a second and get the whole experiment down and have a file system with all this data and stuff. That'd be cool. And the other thing I thought might be cool, which I don't really know much about, but somebody else probably knows a lot about it. DTN could use I'm sure somebody could use a node that could store all kinds of data and then blast it down in a hurry. And then interplanetary. There's a little picture there of Mars. Actually, the laser comm was originally LLCD was originally MLCD. I found out. So they'd already done a lot of work on it for the Mars mission that Bush said we were going to do back in the was that 90s? No, 2000. I don't know. 2000s. Yeah, back a few years ago. Anyway, they thought they were going to do it for Mars. It got canceled. Then somehow they saw that LADEE was happening, and they managed to say, let's put it on LADEE. And it turned out to be a good thing. I think several times when the LADEE was on the axing table, the fact that laser comm was on there, a lot of people interested in that. I think it helped keep the money flowing in to keep it alive. And I'm sure anybody else has any ideas of how it could be used. I'd love to hear it. Except I have a plane to catch at 7:20. So send me an email. Okay, I think that's about it. Any questions? You can get the mic over there. Oh, here it is. I'm sorry. I could do that as long as it doesn't feedback.
So on those lines, so you got your PCI bus, you got the MOAB, and then that's talking to your laser comm payload.
Yeah.
So could you have a mode where the MOAB is basically just sitting there sniffing whatever PCI traffic is on the bus and then just streaming it down in real time over laser comm?
CPCI bus? Sniff? Yeah, go ahead. He knows more about this. He's the CNDH guy.
We looked at a number of different ways of doing that.
Talking that mic.
Is this one?
Oh, is that on?
Yeah.
Oh, okay. I'm sorry.
So we looked at a number of other ways of doing that, and that was one of the modes. The issue was that it was once you turned on the laser comm, you were trying to keep this thing fed. I mean, really, we only used up. It was a TDM kind of situation, so we only used up a 16th of all of the bandwidth, and we are still struggling to keep that one going without saturating it. So in theory, yes, we could have done that, but in practice, I'm not quite sure how that would have been done. So if you're using it for low bandwidth kinds of situations, I'm not quite sure. I think we'd have to think about that first before we start setting that up.
If you scale the power down? I mean,
we could. The issue is that you needed. It's just like any radio. You need enough power to establish link. So that's really the overall situation. We could have. It could be in another situation be slowed down, but I think that the biggest benefit of this is the bandwidth. So that was sort of where we were at.
Very good. Thank you.
I hate to ask this because I know you got a plane, but everybody seems using the DOS file system, so I'm picking on you guys. So what do you really want? I mean, we've got the JFFS2, and we've got another file system that was for MMS, so I'm just curious, when is the fat file system going to die?
Good question.
Yeah, we definitely would rethink that one. As we went forward, the issue is that it was reliable enough at the point, but it's it's definitely one that there's a number of things. We have this whole subsheet of lessons learned that we're all going to sit down and go through that. But that's definitely one of those that we would definitely want to rethink.
Some of it is like knowing your the enemy, or knowing the thing, that it'll work. Not trying
Yeah.
something new, because we didn't have all of this was done with, you have 2 weeks to do this whole thing. So I mean,
In a very small
the other guy,
effort, so.
Scott, could give the more detailed answer, because I think he went in that direction.
When are we going? I know this talk's all about flight software, as it should be, but when are we going to actually hear about this laser terminal and the ground station and the performance of it, and is it going to be a product we can use on other spacecraft and things like that?
There are other missions already planned in the planning phase that are going on. I know that there's several papers and talks that are going to be going on with that. So I know this was the first success of this, and it worked incredibly well. I mean, everybody was very, very pleased, and they were able to use it, basically from day one. It actually worked. We built in all kinds of contingencies on, if it doesn't do this, what do you do? And we never even had to exercise any of those. So I think overall the entire team has been incredibly pleased with the overall operation. So I'm sure that more will be coming at this point.
Yeah, I think the guys that could give those kind of talks are really busy right now.
Yeah, they're still, I mean, we're still an active mission. They're still crunching the data. So I think all of this is going to take some time. So
Again, does it work? Yeah.
Yep.
Again, a question not really software related, but from a Star Tracker supplier point of view, what pointing accuracy did you need?
Oh, geez. Very high. I can't give those numbers. I think Don Borison's paper starts to address it.
Yeah.
We, from LADEE, it drove a lot of, and that was one
Yeah.
of the reasons we had to feed data back. From LADEE, actually Karen, who also is catching a plane, too, she ducked out. We had to get down to a certain accuracy, and then at that point, the LaserCom actually took over, okay? And in fact, the way that the capture works is that they send basically a command up to the spacecraft. And once the spacecraft sees that, it will then start to establish the downlink, pretty much like a regular RF would work. But yes, the scaling up of this it's like hitting the edge of a piece of paper from across the United States is the scaling of that, because it is very, very precise.
It's something like 0.00
Yeah.
something degrees per second.
Yeah.
I don't know.
Yeah.
I'm just guessing. I think it was less small.
Yeah.
All right.
So CPCI, looking at the numbers of like 600 megabits per second, you could see straight off that CPCI would be a real bottleneck. So
It was only 40 megabits per second, but even still, yeah, you can see that.
yeah, so kind of looking at that, I mean, just looking at on paper, that would just stare at you. What other buses or what other considerations would you make if you were designing a system around sort of LaserCom? Because CPCI is kind of everywhere, and everyone thinks, oh, it's great, it's fast, but it has a lot. It does have contention. The protocol itself underneath is pretty complicated, and so yeah.
We actually looked in the early designs. We actually sort of agreed on the 40 megabits per second because it was a very easy one for us to obtain. It was low risk and everything else. There were some faster interfaces, but I do think that a sort of the NVM approach that was going on, and that you would have the actual controller, the memory controller, or the way that we had done it, was going to be the only way that you're going to be keeping these things going. And the way that it gets established, I mean, we able to establish lock, downlink all the data, shut it off, and be done in less than 5 minutes. So that's a very, very kind of quick kind of thing. So you could do this several times if you wanted to, but I think that the only way to do that is to have some kind of dedicated memory with high-speed link that would be able to feed this. I think that unless you came up with another kind of bus or another kind of architecture, but compact PCI is just one of those ubiquitous standards that is flying on a lot of missions.
I think something like Eddie described would work well with a LaserCom, have the FPGAs just dealing with a DMA type approach.
Yeah.
Then you could feed the data, but you still have that bottleneck to get the data onto the card there. I don't know.
Okay, other questions? Yes. Sorry to make you
It's not related to what you've been briefing, but you did mention the end of mission and the ecology, the moon. Do you know what the disposal plan is for this vehicle?
Yeah, pretty much same as
Yeah.
Alcross.
I think,
Very
yeah.
subtle concepts.
Yeah.
Yeah, but actually it's going to make sure it doesn't hit the flag that Neil Armstrong left, and I think there's
Yeah,
a
that's-
Russian landing site, so it still has to, it can't just land anywhere.
But yeah, we're in a equatorial, so we're all along all the other Apollo sites. So we just have to make sure we miss all of those.
Okay.
Okay.
In my mind, it's still a flag.
Any other questions? Nope. Very good. Thank you.